Okay, shall we? Is this okay now? I see the screen, self-healing concrete, a critical appraisal, and I start. Is that okay?
That's perfect. And you just tell me next slide and I will move it forward.
That's beautiful. Very good. Well, I'm very happy to be with you. I call myself a late stage researcher. Eh? You have these early stage researchers, but I'm the late stage researcher. Then, is that okay? Do you hear all of you? Do you hear me?
Yes,
Perfectly.
yes,
Okay.
Yes.
Yes, sir.
Beautiful. The story is that I will philosophize a little bit about self-healing of concrete. I've called it as a subtitle, a critical appraisal, but I submitted my slides first to also to my colleagues Nico Boon and Nele de Bailey and Kim van Tiedelboom. So the whole idea is that we think together a little bit critical about what it's all about, self-healing. And before I start, I like to review a little bit the processes in research. There is what you could call the bottom-up type of research, where you have to ask only one question. I explore a new hypothesis, and if I find something new, hooray, we can then make a publication. This has been the major part of my life. That's the basic research. And that's, after all, easy. It's easy because you have no constraints. The only thing is you have to be original. And that is, it's a marvelous moment when you find something and then you publish, and that's it. A second line of research is that you have to deal with what we now call strategic basic research. You develop something that it has a particular orientation. You still are not obliged to really find something which comes to practice, but it has an implementation. There is some influence from your government that says it should be in this or that direction. And you should try to find something which is at a certain moment of some use to society, strategic basic research. But the strange part of my story is that at the end of my career, I went and started to work together with with a spin-off of the university, which is Avecom. And then you come in a different type of situation, which I thought initially would be easy. The type of situation is that you do have to find an application which fits into the market economy. And that's a bit of a striking event, I must say. And certainly when you are in a situation like today, that there is COVID and nothing goes and you have to survive with the team that is. So it's from that type of background that you will see some of my remarks. That's my introduction. I should maybe add one more thing. Basically, my background is, as some of you may know, I am a bioengineer. I've always worked in environmental biotechnology. And at this moment, I am trying to find microbiological ways to help further in the concept of self-healing. That is the introduction. Next slide. Next slide.
I put the next slide, so I don't know if you see it.
No, I am still on the first.
I think we can see the second one already.
I can do with that.
Now is the second one. Oh no.
Yes, we can see it. We can
Now
clearly
I
see
have
the
it.
second one.
Okay, I have it. Thank you. Is my story clear to everybody?
Yeah, it's clear to me. I see some of them nodding, so I think it is. Yeah.
Okay, I continue then. So the story on self-healing dates for me 20 years back. The story was that at a given moment, Nele de Bailey, which you all know, we had contact, and she said, we have these micropores, we have these small cracks that occur. Can we not in one way or another bring microbiology to help the healing of that? And that dates already 20 years back. Next slide. If you have it, just give me a signal.
Yeah, we have it.
Okay,
So
it comes
you are
soon.
watching the live stream, so that's 10 seconds later. So you will get it.
I will start already.
Yeah.
So the story is that, of course, when you start looking into this concept of self-healing, it's a beautiful concept. There is the self, which is always attractive. Something happens. There is the healing, which is a beautiful word. And then there is the concrete, a massive amount of applications. And then you say, look, what could be indeed the story there? And when you start looking into the literature, you find then lots of information. Here I just referred to the Global Forecast 2021, and I immediately add also a critical element. You look into the world of publications and you find plenty of things, and then you try to find back. That's what I did when I started this story. You try to find back what is the world of application. If you give me next slide, you then see that very large numbers appear, large numbers on the global forecast for 2021. You see there amounts of money which are in millions. That means for me also a lot of opportunities. I have not been interested in money. I've always been interested in jobs, in careers, in possibilities for students. But you see there a tremendous, I think we jumped one slide, but okay. You see there a tremendous amount of money that relates to having this slide, but it is actually not complete. There it appears. We talk about billions in the US and also billions in the EU of job opportunities in repairing cracks. I have to accept that. The next slide is also, if you give me the next slide.
Yeah, it's coming.
Thank you. It also tells you that there are lots of publications. Actually, I'm often a bit amused in the sense that at my age and 10 years out of the actual research world, I'm still, and that's a little bit bragging, but I'm still a highly cited author. If you see me walking, you will see that I walk next to my shoes because I am cited so much. So it gives me the impression of being very important. But the story that I like to bring to all these young people is the publication, the world of publication is something that continuously helps to self-propose and propel what is happening. So there are lots of reviews on this, and if you look in those reviews, you see that indeed there is a tremendous amount of things going on in that concept of self-healing. Yet, once again, talk to practice and you find another perspective. At least that's what I experienced. Next slide. In the next slide, I tell you the story that if you look into these reviews, that of course in this self-healing of concrete, there is the story of the natural self-healing. That's not much what we have to deal about, but you find in the middle of the next slide, if it arrives, you find biological self-healing processes, and that's where we then started to interact. In the biological self-healing processes, you see, of course, there are different aspects, biological precipitation. I think you have heard a lot about this. There are fungi, there are bacteria, there are mesophilic and thermophilic organisms, there are anaerobic. The whole microbiology comes into a very strange world, a world where you deal with concrete. And this is not what biology is all about. So it's actually a totally unpractical marriage, biology and concrete. It doesn't go together yet. A tremendous amount of literature has developed. Of course, there is also this chemical self-healing processes, and some of them have been studied, but we particularly, my particular field, and some of you will deal with this biological self-healing, and that's what I want to focus a little bit further in a critical way. The next slide. The next slide tells you that this is one from the authors of and then the people who work in SmartThings, but I think if you look into their publications, and I cited a paragraph from them, in that publication, they say that the efficiency of self-healing still needs to be further proven under real environmental conditions. So we are already some 20 years in the domain of self-healing and biology, but we also must say that it has to be further proven at this moment under real environmental conditions. To be frank, that's a long time that it needs, so we have to wonder what is happening. Why does it take so long? My story is, there is excellent science in this domain, but the applications are missing. What are the reasons? What is the cost balance? Is the cost-benefit balance maybe one of the problems that we have to dare to address more critically? Next slide. The next slide tells you that autogenous healing, that means at very slow cracks, very low cracks of 0.3 millimeter, that can happen by itself, but the key feature would be for biological healing would be that we can deal with bigger cracks. That would be the thing that we really like to have, and and that we have then the term microbial induced carbonate precipitation. What a beautiful story! Bacteria who make carbonate, and indeed, this all was described and has been further explored in the literature ever since. Next slide. The next slide I have called The Road in Good Faith. And the road started 2000. That's when I started to work on it together with many people. The idea was that we probably, and you see here a number of these points, that bacteria are capable to produce plenty of CO2, for instance, from certain compounds like urea. But bacteria, they produce CO2 normally because they oxidize certain organic matters, and then CO2 is a kind of burning product from them. They burn organic matter, glucose, sugars, and then they produce CO2 just like an engine burns a fuel and then produces CO2. If we give them urea, this is a different thing. There they set free the CO2 because their initial idea was probably to get the ammonia. So we use there a very special reaction of these bacteria. So, oh, this is better. I have now a site, but it comes 5 minutes after I am speaking. I continue with the slides, but there is no synchrony, I think, between the slide and my picture. Is that correct?
No, you're watching the live stream, which is about 10-15 seconds later. So that's why also you see the slides later. But we hear you live, so that's good. So don't look at the screen when you're talking.
Thank you very much. Go back one slide now.
Back one?
One, yeah. Go to the previous one. If possible.
Yeah, it will come up at your screen in a minute.
Thank you.
Now it's there. This one?
It's the road in good faith.
Yeah.
We see the road in good faith now.
Okay, thank you. I'll continue. I don't, but it's a bit of a difficult story. Okay, so the road in good faith, I talk about the bacteria are capable to produce CO2, but it's not their main. It's only when we use it when they are getting profit for themselves that they really do it 100%. So we will use a kind of side metabolism from them. But we know that bacteria, to bring them in concrete, that they have to survive there. But that's a very odd environment for them. Calcium is one of the most destructive elements in biology. It's like a bulldozer for biological molecules. It upsets them. So we have to find new ways or special ways to make them survive in concrete. And the thing that we then have been looking at are spores. Spores are survival structures for bacteria. But what we also have to remember is when we bring bacteria in concrete, it should not affect the strength and the quality of the concrete. So we have to look at that. And then, of course, in order for bacteria to be active, they always need some kind of water and air and nutrients. So that was then also a challenge. When the crack occurs, the bacteria has to be exposed not only to water and air and nutrients, it has then to find a way to come to life in that very odd environment. The next step was then to deal with cost calculations. We first tried to develop the concept, but then the cost calculations are there. And then we did some trials in practice. I give two examples, one from Lab McNell and then one that we tried by talking to some people in the field. I call them the Avecom field tests. And then we are currently, and that's what I will finish with, the question is, what is the perspective for a small and medium enterprise like Avecom developing new bioproducts in this world of self-healing? Next slide. The story that I will use is there have been plenty of PhDs in working on this topic in Ghent and also in Delft, of course. And I will particularly refer to the two latest ones that we had, and that is Felipe Bravo da Silva, who worked on upscaling the production of bacteria for self-healing concrete applications. The idea was bacteria, we can think that they are free, but they aren't free, they are expensive. To grow bacteria in a good way is quite expensive, and Philippe focused on, can we in one way or another deal with these costs, and particularly with the costs of production those bacteria that we need for self-healing. And then the next person that I used some slides from their doctoral presentation is Yusuf Ersan, and he worked on microbial nitrate reduction, which could be a kind of trick that has some additional advantages when we bring the bacteria in the concrete. When bacteria reduce nitrate to nitrite, nitrite can then be an element of advantage because that nitrite can then inhibit the corrosion of the metal bars of the iron which are in the concrete. Let me go to the next slide, which is a mesmerizing slide. The mesmerizing aspect of the next slide is that you see bacteria in front of you. These bacteria, they then seem to excrete calcium carbonate, and it looks like they are doing this with pleasure. But the basics of this mesmerizing, I call this a mesmerizing, that's a little bit the word for misleading, in the sense that these bacteria are suffering at that moment. When they are doing this, when they are taking urea and they are hydrolyzing it, and this urea then produces ammonia, and this ammonia also, and together with the ammonia there comes CO2, these bacteria are under very great stress. They are doing something totally abnormal, and they certainly don't do it with in their normal life this way, and they are then becoming entombed in a kind of calcium carbonate matrix. That idea fits in our project, and we don't have to have mercy with the bacteria. They do something useful, but to us, at least at that moment. But basically, it's not a real natural process. We use something, a sidekick of a natural phenomenon. Next slide. In the next slide, you then see, and you have seen this before, that when you have a crack, and when at the side of the crack there might be urea that comes free and that was present, or there is urea from the outside, and these bacteria are there, then you can have this biologically catalyzed phenomenon, and this crack will fill up. That is well established, and it's beautiful, and you see it happening, and there are many pictures like that, and that is great. But the question that we have to ask is this now really feasible? What are the side aspects? And next slide tells you that to do this, we need to bring in bacteria that withstand these adverse conditions of being incorporated. But bacterial spores can indeed survive for several years and can survive for decades, but under nice conditions. And nice conditions are, for instance, in a soil or in certain tissue. Here we have concrete, and when we deal with concrete, which is such a harsh environment, these spores probably are not, or certainly are not really in a very good condition. So they can, it has been demonstrated, they can improve autogenous healing, but to bring them and to really get them going, we need to protect them, and we need to supply them with nutrients so that when the crack, and when they are at the spot where the crack opens, they come and do something. The next slide shows something that we don't really like to reveal very much. Next slide tells you, look, indeed it works, but if we use those bacillus spores, we must take something into consideration, and that is that it has an effect on the compressive strength of the concrete. That's what you see in the middle of the next slide. The bacillus spores as such, they really affect the strength of the concrete, and only by then putting these spores, for instance, in diatomaceous earth, you can restore this. So the adverse effect of bringing organic matter in general, and then these spores in particular, at a dosage where they really work, that adverse effect on the compressive strength is something that we should not overlook. And that's summarized in the next slide. I like then, the next slide just gives that message, but then continue to the subsequent slide. I'll wait a second, I don't have it yet.
It's coming.
Thank you. So it just summarizes this, but this is an important point. Undesired loss of compressive strength, we have to take this into account. The next slide, which I selected, is then to say that effects like the fact that, thank you, the fact that you see here the width, if you look in the ordinate, the crack closure, as a function, what you see in the abscess, the initial crack width, and you go from A to B to C to D, you see that indeed there is an effect, that there is a better closure when you have the number D, immobilized spores with urea. There is an effect, there is no doubt about this. This is demonstrable, but at the same time, I think also, and once again, I look at with the critical eye, we must say that it's not all that spectacular, and that has an implication to practice, I think. as I will say a little bit further, when you talk to practitioners, yeah, they are hesitating about this. This picture tells you, yeah, there is something, but it isn't all that striking. Next slide. The next slide works a little bit, refers to the work of Yusuf. Yusuf then started also to produce these microbial inocula, and he wanted to produce them in a clever way, a way that these bacteria are then embedded. They are embedded in a kind of matrix, a gel, a kind of granule, which they form themselves. And indeed, that worked out. We worked with a sequential batch reactor. That's what you see here at your left side. And then you get granules. You see these granules of about 500 micrometer. And then you see here the fact that these granules have an inside which is actually anoxic. That means there is no oxygen, and the outside, which is aerobic, and that means that these bacteria are of different nature, can do different processes, and are pretty much by nature, by a kind of jelly matrix, actually protected to do something. And the next slide tells you that indeed they do something. The biomortar, it was demonstrated by Yusuf that it can heal itself much better than, or really be very effective relative to the control. All of that, once again, demonstrating that this is no fancy, that this is reality, and that it can bring something forward, and that here you see the slide, all right, see the slide, you see that the reference mortar, the initial crack, it does not heal so very much if it's wide, but that when the mortar is there and when the culture is there, that's the red line, that it really heals much better. And the next slide shows you that in practice. It is indeed visible.
You have to click more.
Yeah, here you see it.
Oh yeah, there, yeah. Sorry, the bottom part is coming.
Click further, yes.
Yeah.
Please click further.
Yeah.
If you can click further.
Even further?
Yeah, you see nicely that the plain mortar and the biomortar, I think this is very much an illustration of the work of Yusuf, that it can work. Huh? You see at the bottom, the biomortar, how this crack healed. The next slide shows you the principles that are there, the principles which are going much farther than just making CO2. They also demonstrate that you can make things, yes, that you can make this nitrite there at this interface, and that this then altogether can bring to a kind of corrosion inhibition, and a combination of corrosion inhibition and self-healing. If you touch the next slide, I hope it probably is the same one, but it was a slide double in the system. Please go on. Keep going.
Yeah, we see it already.
Yeah, keep going. And keep going to the next slide, please.
The next one, not this one?
That's good. Now, the side effect of urea, but that brings me immediately, I gave already a side effect in the sense that you can really affect the strength of the concrete, but here is now a calculation if we use urea. and we use urea to make as a site, a molecule to bring CO2 into the concrete, and you then start calculating this, as this was something that Philippe did, you then come to the fact that concrete, which contains so much urea over its massive volume to heal the potential possibilities of cracks, that you then have a tremendous amount of ammonia that potentially can get emitted. He put there the comparison that a cubic meter of concrete would then be the amount of ammonia that is produced by 700 cows on a day basis. It's just to tell you that we must look at the whole of the system. We indeed bring forward something, but we then might have side effects that that are not so nice, and that we should not disregard. And in the next slide, we then get the story on economy. As most people had thought that bacteria were cheap, it turned out when you start looking at them, you have to make them, you have to guarantee their quality, that you come to rather, and you have to add them in very large amounts to cover the whole of the concrete mass with that potential of self-healing. Then you come to kind of costs, which you see here, Bacillus sphericus, Bacillus coni, and syrup. Syrup is a kind of industrially produced type of microbial formulation. And then you see that the costs that you really come up with at the bottom, and that is then really, when you do it at the lowest cost possible, that you are with that still at costs of something like 60 to 120 euro that you have to pay for the bacteria per cubic meter of concrete. And that is a hell of a lot of cost, and that is not possible. So that are some of the aspects that you have to put in here into the consideration. The next slide re-emphasizes this in saying that indeed, whatever way you look at it, it costs around the order of magnitude of certainly 10, certainly 100, in the range, certainly 10 to 100. And if you start really looking more carefully, and you take, and somebody has to earn money by producing these bacteria, it is an expensive, self-healing concrete costs around that order of magnitude. So the bacteria are not that handsome in terms of practice. And that brings us to two slides that relate to the other part of the critical assessment. When has it been applied at a larger scale? And it has been applied, this microbial self-healing has been applied by the group of Nele de Bailey in one case, and that means in Belgium, and they have done all kinds of tests on it. That has been well described. That's only very recently. That means with Avecom, next slide, I tried to have some practitioners using it, and they did it because I could convince them, but they were not very not very interested in it. That was I thought that there was a world outside there which would be very happy to take this on board. No, they were not very happy or intrigued. They tried it, and then about 5 months later, they said, I contacted them again, and they said, no. We had to restart all over. They had to cut down it again. They were not happy about it. So that means, and that is my bottom line, I apologize for that, but I think we have to put it in front of us. My general fact finding is that in practice, the interest for self-healing concrete is, at least in my mind, not very large. So once again, when this smarting started, and I was contacted by the people. I said, I'm not saying no, but should we not really question ourselves? Next slide. should we not really question ourselves and practice about the concept? Is there something maybe that we are overlooking? And I took this on board and I talked to a great number of people, actually to everybody who has somebody who wants to talk about it. I talk about it. And the question is, if we talk to the practitioners, they have, and you ask them what could be of interest here, they say, look, what we really are interested is in a plasticizer, something that helps us, that keeps the mortar more workable. That is, next slide, that brings a kind of plasticity to the mortar. We have products, but we would be very intrigued if there would be other possibilities for that. And they talk about these molecules which are available these days. And from what I have learned, these molecules that are available, if I can have the next slide, they are molecules which bring a thin layer around the cement particles and retard the hydration of the cement. And that is then something which helps during the actual making of the concrete, but it apparently might also help to give some elasticity in certain moments to the already hardened cement. And when you look into the literature, and I saw it only recently once on a BBC channel, they say, look, why is the Chinese wall so strong? It is because during the building of the Chinese wall, they use some amylopectin, which is the kind of, when you boil rice, when you boil rice, you get an amylopectin in the water, and that, when you integrate that in, to some extent, not too much, into the cement, you get a better cement. And the same you can do with carrageenan, which is from marine origin, or with lignosulfonates. But the miracle that has occurred is that the chemical industry has found polycarboxylate ethers, PCEs, which are made from acrylamide and which are stabilized by a microbicide, benzoisothiazole, and that is a magnificent product. Next slide. This product, that is what the people from practice say. If you could find something which is of biological origin, which is not containing this rather I'm not saying toxic, but it is not a pleasant microbicide, that would be beautiful. That is the story that I got from talking with people in practice. They say, look, this is a beautiful product, no discussion, but it is expensive and it contains this chemical that irritates the skin of certain people. Next slide brings me then to what I have identified, and I like to discuss with all of you for the field of practice. What I have identified as a niche is develop a plasticizer, an alternative plasticizer, which immediately has a visible effect to the practitioner, because it has that plasticity in the system, and which maybe at a later stage, when cracks occur, becomes the site where the microbes from nature, from the outside or from the inside, I don't want to specify it yet, but microbes can start to grow and do a healing job. So I talk about the concept of a plasticizer facilitated self-healing. That was some kind of a, let's say, a consequence of talking with so many people, and that was the positive message I got through that. Of course, you don't have to agree with that. You can fully criticize it, and you have the full right to completely disagree with this. But what we need to do that is, and it's not easy, to have a plasticizer which is as effective as this master chromium and at competitive costs, which means that you have to apply it at a few euro per cubic meter of concrete. And it should have a product which does not influence the strength and can be accepted straight away by the regulator. The regulator is also a very important element. When I talk to people, they kind of always say, yeah, but to introduce something new in the world of concrete, the regulator is there and you have to immediately guarantee that it will work for 50 years onwards. That is not an easy thing. And then the product should, that's the third criterion, it should be stable, probably, but preferably not contain this toxic or, let's say, less appreciable microbial side, and indeed induces, and when a crack occurs, it should enhance microbial colonization, which then would be of good use, a kind of secondary effect to the primary effect, which would be the plasticizer effect. The all but last slide, the next slide. I return to my story of my 20 years of good faith in this development. What perspective can a small and medium enterprise like Avecom have at this moment in developing a bioproduct which would fit in this configuration? That is the question that I have now to see in the concept of smartings. And I must be honest, an SME, it has to survive and to develop something that has no direct application or will have an application maybe 20 years from here, that is not possible. So the last slide of the story says, how do you address this? And I think the good way is that you start as an SME to look at the pull side. Avecom is developing bioproducts, but the question is, if you then talk with people from the cement and concrete industry, is there a pull? The push could come from Smartings and Avecom, but the pull is these concrete firms. Are they really intrigued? Are they saying, are they eager? Is there any type of eagerness in that world to take on a kind of new type of bioplasticizer? And if not, we have to admit, then that's the end of the line for an SME in this story. If there is a pull, then the push can be to look at different biomolecules and their effect on the microbial colonization and the concomitant healing of the dust-treated concrete. That's then very clear. But I am in search for, let's say, with the last 3, 4, 5 months, to get in contact and with all your help and your good faith, to find people, to find an industry, to find an application area where there is eagerness for this concept. And eagerness means very simply that people say, yes, we want to apply it immediately. Please give us 20 kilograms of your product and we try it out. That's for me eagerness. So this is the end of my rather difficult presentation. I apologize that it was sometimes a bit retardation, but I hope that you have had a message. I'm once again, it's not so that I don't believe in the concept, but I think we must try and dare to address new perspectives for it. Thank you very much.
Well, thank you very much, Willy, for this clear story, very clear. And I think there is something to discuss now. So I would like all the ESRs to open their camera and their sound and then start discussing. What do you think about this? What is the future of self-healing concrete? Who dares? Nobody yet? Can also appoint someone. Or Tim can start with his views.
Sorry, I missed that last part. Was it addressed to me?
Yeah, I thought maybe you can start the discussion.
Yeah, I think that we need to be perhaps realistic and need to think on can we indeed apply self-healing materials in all? Yeah, the answer might be no. We don't need self-healing concrete when we are building like a regular house. But maybe it is good if the ESRs can think there are a lot of specific situations where indeed a lot of engineers with a lot of experience have to come in and to think about the very specific boundaries that these projects like specific bridges or tunnels have. And can you maybe think about what kind of techniques we could apply in these specific engineering practices?
Yeah, and then probably also think about indeed applications where if you get damage, if you get cracks in the structure, they cause really hindrance, or the functionality of the structure is lost, and applications which are difficult to repair, because if they are underground, you cannot access them, then they are probably willing to spend more money on it to really make something that is repairing itself. So then it's becoming very important, because then it can save a lot of money if you have something like this built in. But yeah, that's something they have to realize, and yes, most of the time they don't want to invest in something like this, which might happen in the future. If they know it's going to happen, if they know they will get damaged, then they will spend money. But if it is just a risk analysis, that's sometimes difficult.
Yeah, perhaps I can give maybe a concrete example which would make it easier for you. If we look now at the building sector, we see that for certain more complicated projects, we go to design, build, finance, and maintain agreements. So where the contractor really has to maintain the structure that he has built for example, 10 years or something. Now, let's say that the contractor builds a swimming pool. So this is really a large bulk of concrete, and there are cracks in this concrete. Now, as a result of these cracks, the swimming pool is leaking. But in a lot of contracts, it is stated that, for example, the pool cannot leak. So what then has to happen? The contractor has to come in. He has to send a diver into the swimming pool to repair the cracks. They then have to wait for a week or two, and then the owner of the swimming pool says, okay, it is still leaking. Contractor, do something about this, fix this problem. The contractor then has to contact the diver again. The diver has to go again to the same location, perhaps another location. The diver has to go in, has to repair the material again. They have to wait again. It has to be evaluated. So you can see that this becomes, in the end, a very expensive process. So perhaps in a case like this, self-healing concrete could, despite its higher cost, reduce the overall cost of the project, because maintenance would be considerably. So this is maybe one example. So it would be good for all of you to think about other examples.
So who has a nice example and can join to the discussion? I know it's almost lunchtime, but still.
We get hungry. What do the people think about the double feature of, or the workability first, a straight effect, and then self-healing which follows?
I think that would be a very good idea to have it also indeed working as a plasticizer, that it controls the workability, and then also maybe the has influence on the early age hydration, that it works also to keep the moisture inside, that you have the hydration in a correct way, that you don't lose water at the surface. So that could indeed be very useful if it also has that function.
Have you done in Delft already research on that? I think I know that there is in Holland the development of that sulfated polysaccharide type of polymer extracted from sewage sludge and the combination with concrete. Could you comment on that, Henk? Or
I think Henk is not anymore. No, Henk left. So I know that there is research going on, that they developed indeed some curing compounds made of this sewage sludge. And also Henk is with a PhD student, Emanuele. They are working on using the sludge also, the bacteria in the sludge to work as self-healing agent. So they are doing research on that, but that's still not into application yet. So
okay. Because there the cost factor would be lower, and it could have the same type of double approach. That's what I'm trying to hint at.
Yeah. Yeah, I think that's a very good idea, because then it will, with the double approach, then they see the benefit of using it in the early stage as plasticizer. So then that really works. Yeah, I see that. You already think about applications now? You had time to think? Where do you see that bacterial concrete would be useful, and still you can earn money with it? Because that's important. Or maybe what Sean is doing now, that could, because Sean is working in the project, in the SmartThings project, and he tries to put the self-healing agent, whatever it is, but he tries to put it only in the cover zone of the concrete. So the outer layer, only the outer 5 centimeters, let's say, because there you get the cracks and you have to block the cracks somehow, that the water and ions cannot go in. So that means that you even could put higher amounts of healing agent in that zone and still not put it in the bulk of the material. So then it that might be a solution to make it more economic, because then it would only increase the cost of the outside layer, but for the total cost of the structure, it's maybe not that much then. So then that could probably be a solution.
Yeah, I'm also maybe thinking about sewage systems. where you, on the one hand, have a very high chemical load, which degrades this, but on the other hand, there are also bacteria which are degrading this concrete. So if you could apply a self-healing agent, which would provide a cover for example, for the concrete to prevent it from degrading from the bacterial attack that you have in sewage systems, would also be a certain aspect which you can take into account. Or as Hank was saying, like if you apply self-healing agent in the concrete cover zone, this could be, for example, very useful in certain bridges, where if you have to apply cracks in these bridges, how will you do this? This is not very straightforward. You would need to close down the road which is underneath, which has a huge economical impact, because you are basically disrupting one of the major transport roads probably of your country.
Now, going to your first point, Tim, maybe Willy can answer that because he is the specialist. Are the bacteria that attack the concrete the same as the bacteria that can repair the concrete? Probably not. And are they going to fight with each other? I don't know. You are the expert, Willy.
Well, bacteria are endless in their variations, but normally those who attack the concrete, they are basically bacteria. What happens is that in the sewer, H2S, that's the rotten egg smell that comes out of the sewage and condenses at the top layer where there is oxygen, and then some bacteria make their living by oxidizing this sulfide to sulfuric acid, and they really make sulfuric acid. And that sulfuric acid then, of course, breaks down or gives the ettringite, gives calcium sulfide, which breaks up the concrete. So no, they are not the same, but there are it's a good idea to, and there is a tremendous problem, particularly in countries, not in our cooler countries, but in countries where sewage is of high temperature and where the summers are hot. There you have a lot of H2S in the sewers, and there can be tremendous damage. But there is another element. You talk to these people, and this type of consideration is that it might happen 20 years from here, 30 years from here. So who cares? That's the story always. I don't care. This is for later. So we are a short-sighted type of market economy who doesn't want to take that very easily into account. That's my experience.
Yeah, and that is stupid with our concrete that lasts so long. Eh?
Yeah.
A mobile phone lasts maybe 2 years, and then people are willing to spend some more money to extend the lifetime. But anything for that lives that long, like 50, 100 years, who cares indeed that if something happens then? That's a problem.
That's why I return to my first point. We must try to think in self-healing of something which is visible immediately. And then it will catch on. You must have an immediate effect that people say, oh, yeah, we have this, and then later on it will also be a good thing in the concept of corrosion, in the concept of self-healing, in the concept of being resistant towards sulfate producing bacteria. That secondary element they are willing to take on, but there must be a first effect.
Mm-hmm. Yeah. Yeah, that's true. It's if the self-healing is secondary, then they will accept that, but there should be a first thing. That's true. But
I can be fully wrong in this idea, but that is what comes out by talking to people.
No, that's true. But then maybe it would be effective. For for structures that get cracks already after 1 or 2 weeks. So massive concrete structures that get this thermal cracking that happens after 1-2 weeks, then they would maybe accept it. So if you can prevent that one, because but if it takes indeed 20 years before they see an effect, then then that will be difficult to sell it. I see.
So my message for today is, I'm all for self-healing, but we must have an element that triggers the application at a very early stage, the self-healing and all the secondary things which are good for concrete. We must try to put them at a later stage. We must actually, if we are believing in our world, we must have an effect and program that effect earlier on. Then we will have applications.
Yeah, at least then it's much easier to sell.
Yeah.
Now of course, we see also the benefit for if it only repairs something after 20 years, but that's not easy to sell. We have to convince those owners or those contractors to do that, and that's not easy, because that's a problem with buildings also. Contractors, they don't think for 30 years, because they only build it and then actually they sell the building to the owner, and then it's yours and do whatever you want with it. But maybe you can convince them if you have contracts that they have to indeed design it, build it, but also do the maintenance, and maybe also finance the whole procedure for the whole lifetime. So for 30, 40, 50 years. So then maybe it becomes interesting for them. But then you have to change the type of contracts that you are giving out to build structures. Someone else that wants to comment? Looking to all the pictures. I think they're all ready for lunch already.
Okay. I don't know if Esteban is listening. Esteban, are you listening?
Maybe he's in the live stream, but then we cannot hear him. So.
Okay, but I am. This is my point of view. I'm open for further contacts and emails and discussion, but I will continue to work on that link with practice. I think this is very important that we continue that. Yeah,
I completely agree with that. And maybe we can discuss more on Monday. Then we have a project meeting. So maybe you're also there. So
no, well,
okay.
At this moment, I try to keep that SME, how can I say, it's under oxygen, extra oxygen. It has a COVID attack, and I must try to.
Okay, that's not easy in these these situations, But then I would like to thank you very much for giving the talk today, which was not easy. The connection and the time difference of a few seconds or 20 seconds. So, but still, you managed quite well. So it was very interesting to have you and to have the discussion with you. So thank you very much for that, and well, we talk to you later and see you later in the project.
And thank you for all the good help, Eric, and greetings to all.
Yeah, okay, thank you. Goodbye, Willy.